Hey everyone, welcome to this episode of KuTube. Before we begin today, please make sure you have the following materials out. For today's lesson, you're definitely going to need a copy of today's notes as well as a pencil. Are you ready? Let's begin. Today we're going to be really focusing on characteristics of quadratic functions. A lot of the work that we've been doing in our last unit is really going to be culminating in today's lesson. Today's goal is going to be able to identify characteristics of quadratic functions. By the end of today's lesson, you should be able to describe and identify how values of a and c affect our parent function. Before we begin talking about characteristics of quadratic functions, though, it's going to be really important to review what a parent function is. So, as you see on this page, we have a lot of pictures of different parent functions. A parent function is the simplest function that still satisfies the definition of a certain type of function. We've done a lot of work with linear functions, and what we have here as I zoom in on the board is f of x equals x. That is the parent function for every linear function we dealt with. Now, as we looked through linear functions and we looked back into slope-intercept form or point-slope form or standard form, we know how to affect that parent function. By changing the slope, we kind of change the rotation of the graph. By changing the y-intercept, we translate that graph up or down on the y-axis. We've also spent some time in class talking about absolute value functions and how when we change our a value in our absolute value function, it affects how wide or narrow our absolute value function is. So similar with linear functions and absolute value functions, in this whole unit we're going to be dealing with quadratic functions. And what we have here is our simplest quadratic function, or our parent function for our quadratic function, which is f of x equals x squared. And as we give you all these different types of quadratic functions throughout this unit, we're always thinking back to this parent function. And how are we translating and transforming our parent function into that quadratic function that's given? So let's begin. The first thing we want to talk about is what makes a function a quadratic function. Now, in our last unit, we dealt a lot with quadratic polynomials, all right, specifically quadratic trinomials. Now, if I focus in just here on g of x equals 10x squared plus 27x, we were given a lot of quadratic expressions in our last unit. Now, as we start to set this equal to something, and in this case g of x, we know that we're starting to deal with the relation, right? We input something in for x, we get something out for g of x, and we're starting to go back to the idea of input and output values. So we're really taking a look at how we're taking a lot of the skill sets that we did in our last unit and now transforming it into functions, specifically quadratic functions. Now on the left-hand side, we're going to see a lot of examples of quadratic functions. And let's just go over some basics. Well, we know the first one is a quadratic function because that's our parent function. It's the simplest form of all quadratic functions. And what we simply did here is just add plus 27. Now, if we take a look at the next example, y equals 3x squared minus 5x plus 7, we're dealing with that quadratic trinomial, but now setting it equal to y, forming that relation, forming that function. But don't forget, we don't necessarily just have to have whole integer values, right? We also could have rational numbers, so we could have decimals and fractions in it. I could also give you guys quadratic functions where it's not written in standard form. I also could give you quadratic functions where it's written in factored form. I could also give you guys quadratic functions where there's variables on both sides. So as we take a look at all the examples on the left, these are still all examples of quadratic functions. Now that we have a good understanding and a good idea of differences in quadratic functions, let's take a look at some non-examples. Now this first example that we're going to take a look at is clearly not a quadratic function, because my highest degree is 1. If my highest degree is 1, we know we're dealing with a linear function. So this is obviously not quadratic, it's linear. If we take a look at the second example, well, it's also not a quadratic function, and neither is the third one, because our highest degree is not 2. We've looked at absolute value functions, thinking back to our parent functions, that's clearly not a quadratic. And this last example is a constant. So there we have it. We have some examples of quadratic functions, and we also have some examples of non-quadratic functions. So now that we've looked at some examples, let's actually create a formal definition. A quadratic function is a nonlinear function that can be written in the standard form y equals ax squared plus bx plus c. reiterating that idea, we've been dealing with ax squared plus bx plus c. We've been classifying that as a quadratic trinomial. But the moment I start to set that equal to y, we're now dealing with a function. We have input values, we're doing something to that x to get to that y value. Now notice it does say that a quadratic function must be written in the standard form y equals ax squared plus bx plus c, where a does not equal 0. Why do you think a can't be 0? Good, because if a is 0, this whole entire first term will cancel out, leaving us with a linear function. So in order for it to be a quadratic function, I need to have a not be equal to 0. We need that leading coefficient there. Anytime you guys are graphing a quadratic function, it's going to form a U-shaped graph, which we call a parabola. So before we get into today's notes, let's look at some common misconceptions. Now Olivia says f of x is equal to 4 plus x squared plus x is not a quadratic because the first term is a constant. Chelsea says that g of x equals 2x squared plus 1 is not a quadratic because it does not contain a linear term. Let's go into this first common misconception. Now Olivia says this is not a quadratic because the first term is constant. Does that matter? Good. No, it should not matter here because we know if we take that same function, write it in standard form, we now know we see that first term has highest degree of 2, which creates this as a quadratic function. So Olivia is not correct in this case. Sorry, Olivia. Let's take a look here. Chelsea says that g of x equals 2x squared plus 1 is not a quadratic because it does not contain a linear term. Well, when we talk about our linear term here, right, going back to the idea of ax squared plus bx plus c, that linear term is the one that has the highest degree of 1. Does it matter that it doesn't have a linear term? No. In this case, my value of b is 0. So we have g of x is equal to 2x squared plus b of x, which is 0, cancels out, plus 1. This is okay. This is still a quadratic. My highest degree is 2. So our focus of the lesson is to really start to pinpoint characteristics of a quadratic function. We've talked about how the parent function of a quadratic function is f of x equals x squared. Every graph that we're going to be exploring here in this unit will be the graphs of all other quadratic functions that are transformations of the graph of the parent function. So we clearly have a picture of the parent function, f of x equals x squared here drawn. Now, throughout the unit, we might be moving that graph up. We might be reflecting it over the x-axis. We might be sliding it to the right. We might be sliding it to the left. We might be making it wider. We might be making it really narrow. So as we're going through, what we really want to start thinking about are characteristics of the quadratic function and how we can start to pinpoint key features that will give us clues into the transformations. Now, the first thing we want to talk about is some key vocabulary. The lowest point on the parabola that opens up or the highest point of the parabola that opens down is something that we call the vertex. Now, as we see in this parent function, my graph is opening up. Since it's opening up, my vertex is that lowest point of that U-shaped graph. Now, remember, whenever we're reading a graph, we kind of start from the left, draw our attention down from the left, and then back up to the right, okay? So when we're looking at the vertex, in this case, my vertex is a min. And our specific vertex is the point 0, 0. The next important piece of vocabulary we want to talk about is the axis of symmetry. Now, the axis of symmetry is the vertical line that cuts or divides the parabola into two symmetrical parts. The axis of symmetry will always pass through the vertex. So in this case, what is my axis of symmetry here? Good, y equals 0. Now, when we think about the words vertex and then think of the words axis of symmetry, this should be leading us back into a specific unit we kind of talked about. That's correct, absolute value functions. So as we're going through some of these quadratic functions, really starting to look at some similarities between quadratic functions and what we've learned about absolute value functions. So today's goal is to really explore how A and C affect the transformation of a quadratic function from its parent function. Now, in all of today's example, we're really going to be replacing b with 0, which is going to eliminate this middle term. And it's not because b isn't important, it's just because we really want to first and foremost focus on the effects that A has on the transformation and the effects that C has on the transformation. So, let's move on to today's notes and let's explore what happens when we graph our parent function. Now, going back to basics, we have y equals x squared, and our goal here is to graph this parent function. Now, obviously, we can plug it into Desmos, we can use a graphing calculator, but we want to go back to this idea that this is a relation, right? And when we're talking about that relationship between x and y. And what we're doing here is we're going to start by creating a table of values to see how we can graph a quadratic function. Well, as you note on the left, on the left-hand side here, we have some input values. We just made some input values up, and now we're going to figure out what the output is. So when I input in -3 into my parent function, the first thing we can do is kind of solve that out. That power of 2 belongs to the value of x, so I need to put that in parentheses. So when x is -3, my y value is 9. So we're left with a point -3, 9. When my input value is -2, we're just going to do the same thing here. My output value is 4, so we're left with -2, 4. When my input value is 0, well, that's 0 squared, which is 0. Ooh, so we notice that this is going through the origin, which we could kind of have predicted since it is the parent function. We're going to continue with my input value of 2 squared, which gives me 4. So we're looking at 2, 4. And then finally, 3 squared is 9, so this last point would be 3, 9. Now that we've inputted in those 5 different x values, let's graph all of these points here. So I'm going to start with -3, 9. As I'm doing it on my paper, you can do it on yours. Okay, trying your best to create that nice parabola starting from the left, moving to the right, indicating with arrows that continues on infinitely. Now looking at the graph above, what shape does it make? Sure, it makes a U-shaped graph, but the correct terminology is it forms a parabola. Now we're going to look at that vertex. Now remember that vertex is that maximum point or the minimum point, and in this case, since the graph is facing upwards, it's at minimum, all right, and it's that turning point of the graph. So my vertex here is 0, 0, and since it's the lowest part of my graph, it's a minimum value. Finally, we're going to look at domain and range. Well, remember there's 2 different ways that we can express domain and range. We can do one as interval notation or we can do set notation. It is asking us for interval notation. So if we scan our graph from left to right, we can see that there are all values of x values that would actually have a y value in this function. So my domain is all real numbers. And my range, I'm scanning from the bottom to the top. Well, we notice here that my smallest range value or my smallest y value is 0, and then it continues on infinitely. So we're going to say our range is inclusive of 0 to positive infinity. If I did write it in set notation, which we don't need to, I'm going to do it here on the bottom, that would be -infinity to infinity. All right, and we'd have the set of values of y is greater than or equal to 0. All right, now that we've taken a look at this parent function, let's start to explore how changing the values of a and c start to transform our parent function. So you're going to use the rest of the notes, and what you're going to do right now is you're going to go onto desmos.com/calculator to graph and draw a sketch of each function shown on your notes. Use what you discovered to answer questions regarding the a term and the c term. As you're thinking through all of these examples, really thinking back to how our a and c values affect our parent function. How is it transforming from the function that we just drew here? Once you're ready, you're going to pause the video and go ahead and complete the rest of your notes. All right, at this point, hopefully you've completed the rest of the notes. You're going to take a moment and actually take a look at how some of these values have affected our function. Now, on the first page here, we actually started to explore values of a, and you're going to see our vertex in the first example, y equals 6x squared, right, was 0, 0. It's a min value. Our domain is still all real numbers, and our range is 0 to infinity. However, we noticed that the graph faced upward, and it was more narrow. Remember, that's that vertical stretch, bringing our arms really high up above our head. Now, we noticed that when we changed our a value to -2, well, our vertex was still 0, 0, but it now became a max. Our whole quadratic function started to reflect over the x-axis, and it was still narrow. It was still a vertical stretch. So for these two first examples, what did we notice that happened to the graph as the coefficient of x squared changed in the parent function? Well, we should have noticed that when a is positive, the graph opens upwards, facing upwards above the x-axis. When a is less than 0, or a fancy way of saying that, just a is negative, the graph opens downward. As you continued, then we started to change a little further. We created rational number values for a. And what we should have noticed here is that in this case, when a has a fractional slope, the graph becomes wider, or we had a vertical compression. When a was an integer, the graph was more narrow. We had a vertical stretch. Have we heard some of this terminology before? Yeah, that's right, through our absolute value function. So we're starting to see a lot of similarities there. The next thing we really explored was how c started to affect the graph. So taking a look at this first function, y equals -x squared plus 1, well, right off the bat, we notice that a is negative, so our graph is facing downwards or reflected over the x-axis. And now we notice that we had a +1 here value for c. Well, we do notice that the value of c shifts the graph up or down, similar to how our b value in our linear function shifted our graph up and down on the y-axis. So as you went through it, we started to notice a lot of things. A affects the following three things. It affects whether or not the graph opens up or down, whether the vertex is a min or a max, whether the graph was narrow, vertical stretch, or wider, a vertical compression. When we started to look at how c affects the graph, well, c tells us our y-intercept, it tells how the graph shifts up and down, and it also gives us insight into our vertex. So, as we start to explore different functions, we really should be making predictions about what the graph is going to look like even before graphing it. So if I gave you a function like y equals -3x squared minus 5, right off the bat, we see that a is negative, so it opens down. Since a is not fraction, it's an integer, it's a little bit more narrow. Since it's opening downward, my vertex is a max. We also can start to notice that it shifts down 5 units because my c value is -5. The vertex is at 0, -5, and my y-intercept is at 0, -5. And then obviously it's a parabola. Knowing characteristics of the graph can really help us to determine what the graph looks like without actually having to graph it. So let's generalize some statements here. And although this is not in your notes, you might want to kind of record this down. A tells us a few specific points about the graph. It tells us whether or not the graph opens up or down. If the graph is opening upwards, we're dealing with a min value. If the graph is opening downwards, we're looking at a max value. We also know that when we are looking at A, it tells us if it's a vertical stretch, stretching those arms up really nice and high above your head, or is it a vertical compression, a little bit of a wider graph. C value of our quadratic function also tells us a lot of important information. More specifically, it just tells us if we're shifting the graph up and down, which really affects our y-intercept and our vertex. We've done a lot of work today with quadratic functions and identifying specific characteristics of quadratic functions. We looked at some key vocabulary: vertex, min, max, axis of symmetry. We also reviewed domain and range, and more specifically, we really focused how A and C really affects the graph. I hope this lesson really helped to kick off of our unit for quadratics. Thanks for watching. Hope you have a great day.